Hello everyone, it's Sebastiano Stipa. Welcome to the fourth tutorial of the Dynamic Mesh series. Today we are going to see how to use the SolidBody motion solver together with the Arbitrary Mesh Interface, the AMI, in OpenFOAM in order to rotate the same airfoil of the previous cases. First, let's talk about the method a little bit. Here we will basically split the mesh of the airfoil in two regions with the axisymmetric geometry, which is a sphere or a cylinder. In our case, we'll use a cylinder because the case is 2D. So we will define two regions in the mesh, which are region 0, which is this circular region where the airfoil is enclosed, and the external region, which is the base mesh that we used in the previous cases, minus this region 1, let's say. So why we will define these two regions? Because basically we will apply the SolidBody motion to this portion of the mesh, the inner circle, so that it will rotate rigidly around the point which will be defined by ourselves, and simulate the pitching of the airfoil, just like this. So this approach is very useful. In this case, we use the same mesh as the previous cases, but it's not very, let's say, indicated for this application, because you see that the wake zone of the mesh is rotating with the cell zone. So in order to use this approach, we would have to change the mesh a little bit in order to ensure accuracy in the inner portion of the mesh. So let's have a look at the case. This is not a difficult application, a difficult problem using the AMI and the SolidBody motion solver, but we have to work a little bit with the mesh because the meshing process is the most difficult part for this tutorial. So we have the 0.orig folder, which is the same as the previous cases, where the initial condition and boundary condition are set. Then we have I created a logs folder where all the logs will be put. Now it's empty because we didn't run anything. Then we have a master and a slave case. So I will explain them in a moment. And then we have the solution folder where the solution, let's say the case containing the solution, will be put. And these are automatic script in order to, let's say, have a automatized procedure. Here in this tutorial we will go step by step, but just by running all the case will run, and then all clean will clean up the case. And then we have the usual initial condition that I like in order to parameterize some input data, which is the same as the last tutorials. So the idea is to create two different meshes, as we would run two different cases, and then merge the mesh together and put the resulting mesh into the solution folder, defining a case which will be run with Pimple Foam. So in these two folders, then there is let's say a case properly without the zero boundary condition, the zero folder, because we will not solve anything inside these two folders. So let's have a look inside the master folder. We have the constant and system directory. And in the slave folder as well, we have the constant and system directory. These two folders are really the same, except from one parameter, for some parameter, which I will explain in a second. Let's now have a look at the process in order to start dealing with this case. So we'll enter the master case, and then we will copy first the initial condition. Okay, so now let's run block mesh and let's see what happens. I will anticipate this is the same mesh, the same block mesh with respect to the previous tutorials. So it'll run fine. Just to show you. This is really the same mesh with respect to the other cases, defined exactly like the other cases. So now what we're going to do is to use the SnappyXMesh, the OpenFOAM automatic mesher, in order to extract a subregion of this mesh. So we're going to define a cylinder inside the SnappyXMesh, and then tell SnappyXMesh to extract the inner part of the mesh. The inner part of the mesh with respect to the cylinder. So we are going to use SnappyXMesh, which is located in the system directory, the SnappyXMesh dictionary. So let's have a look. SnappyXMesh goes through three main processes, which are the castellated mesh, which is something like a Lego building. Like the mesh is splitted, the cells are divided in cells which are inside the geometry and cells which are outside the geometry, because in SnappyXMesh we have basically almost always to define a geometry. And then SnappyXMesh will remove the cells which are not, let's say, trespassed by the fluid. So where there is fluid, SnappyXMesh will keep the cells, and where there's not fluid, SnappyXMesh will remove the cells. So how do we tell SnappyXMesh where the fluid is? There is one parameter, which is the thing that changes between the master and the slave case, which is the location in mesh. So given this point, which is a point, every cells which is connected to this point without crossing, let's say, a surface, a watertight surface, will be kept, while the other cell will be removed from the mesh. Then there is the add layers procedure, which is false in this case because we are not using add layers. So in this case we are not exploiting the full potential of SnappyXMesh. We are just using it to extract a portion of the mesh. So we define in the geometry section, we define a cylinder, which is a type searchable cylinder, pretty like the way we define the cylinder in the block mesh. Yeah, this cylinder is has its axis in the middle of the airfoil and a radius of 2. And it's the cylinder which will delimitate the inner portion of the mesh with respect to the outer portion of the mesh. And it's crossing the mesh entirely. You see that the y it's minus 1000 and plus 1000. So we can call it watertight, which means that it split the mesh in two regions which are not connected. If you put fluid in one region, the fluid will stay there and will not go into the other region. So this will be useful in order to tell SnappyXMesh which region to remove or keep with the location in mesh parameter. So having defined this cylinder, we have also to, in order to let this cylinder be created as a patch, specified it in the refinement surfaces. We specify the name of the patch which will be created from this cylinder with a 0 refinement level in order to just extract this patch without any refinement. And we say that this patch is of type patch, which is a general type for patches in OpenFOAM. We now, the snap control are the same as any tutorial. You can have a look at the motorbike tutorial. And the add layer control is really ignored by SnappyXMesh, by OpenFOAM in this application. Then you see that there is an include mesh quality dict, which is a file located in etc in the OpenFOAM directory, and I copied this file inside the system directory. So let's see what happens if we run SnappyXMesh. We add the overwrite option in order to let OpenFOAM write the mesh without increasing the time step. So it's very quickly, as you see, because it only has to remove a portion of the mesh, and without doing any refinement, any layer addition, any more complex operation. So what we got here is that we extracted the portion of the mesh, the inner portion of the mesh. So now we'll have this patch, which is called master, as we can see from this menu. If we highlight only the master patch and the airfoil, we see that this is the master patch. Then we have the airfoil, and then we have the back and front, and then we have the wall group, which is the airfoil, I guess. Yes. So you'll see that by doing this manipulation to the mesh, OpenFOAM deleted all the, let's say, all the patches, all the boundaries that we defined within the block mesh dict. And also you'll see that SnappyXMesh did some modification to the mesh, deforming it and adapting the cells to the cylinder geometry. This is no more, let's say, this is no more the mesh that we had after the block mesh, but it is a little bit deformed, as you see. Then we go into the, we do the extrude mesh in order to be sure to have a single cell in the infinite direction. Let me first load the OF8. Oh yeah, it has not the option override. Okay. What is this? Okay. And then we will have a check mesh. Okay. So you'll see that we have, in this case, number of regions 1. After the merging process of the two different meshes from the master and the slave case, we'll have number of region 2. I will say that this is fundamental in order to use the AMI approach. So now let's go to the slave case, and let's copy the initial conditions. Okay, and rerun the block mesh. And as you can see, this is the same with respect to the master, let's say case, to the master case. It's really the same. And then we will use the SnappyXMesh in order to extract the other portion of the mesh. I'll put the two SnappyXMeshes, the two SnappyXMesh files, one next to each other, in order to let you see the differences between them. So they are the same up to here, where in the master the boundary patch, the circular patch, is named master, whereas in the slave case the circular patch is called slave, but the cylinder is really the same. Then we have the other difference is here, when we go to define the patch and the type of patch. And then the third difference is in the location in mesh point. So we see that here it is located inside the cylinder, whereas here it is located outside the cylinder. So OpenFOAM will extract all the cells outside of the cylinder. So let's run in this case this SnappyXMesh override. Okay. And you'll see that here we extracted the other portion of the mesh. So don't mind about the fact that I used the same mesh. This is in order to simplify things, but it's really the process which matters in this case, the process which I am using. So now note that this patch is called slave. This patch is called slave. So this is the slave patch, which is overlapped with respect to the master patch, and as before, OpenFOAM removed those patches which are not inside the mesh. So here you see only the back and front, the free stream group, which is inlet plus outlet, the slave patch, and the internal mesh, which is the whole mesh. So now we're going to merge these this mesh with the inner mesh, and we're going to use the utility mergeMesh. So mergeMesh comes with some options, which are this one, and then you have to specify the master case and the add case. So in our case, in order to be clear, we're going to copy the content of the master folder inside the solution folder, which will be the location where we are going to run the simulation. So we are going to the solution, which is empty, and we are going to copy everything from the master to here. Okay, now we can run the mergeMesh application. Let me be sure that okay. mergeMeshes override, and then we'll specify the master case, which is this one, so we'll put a dot, and then the slave case. Okay, so it finished correctly. Now you'll see that we have 7 patches, the airfoil, the back and front, the master patch, the slave patch, and the inlet and outlet patch. So in order to use the AMI, now let's have a look at the mesh before doing anything. Okay, we missed something. We missed the extrude mesh into the slave case. So you see that the meshes are not well overlapped, because mergeMeshes, one thing that is really important is merging the 2 meshes, but is not merging the regions. In fact, if I go for check mesh here, you'll see that we have 2 regions. Anyway, let's do the extrude mesh, and then back to the solution. And then we'll go again for mergeMeshes. And now you'll see that they'll be correct. Yeah. So you'll see that mergeMesh merged the 2 meshes, but still you can see the interface here, and still are present the slave and master patch, which are now overlapping. So this one and this one are 2 distinct regions in the mesh. Now we are going to create the arbitrary mesh interface, and we're going to use the createPatch utility, which has its own dictionary, which is inside the system directory. And basically here I specify which are the patches that I want to create which type are they and the way I want to create them. So here I'm constructing from patches, and I choose the master patch in order to create the master AMI, which is a type cyclic AMI. And I have to put these parameters here. These two are not really useful. And the transformation is a very important parameter which can allow for different treatments of the patch. Here, since we are not dealing with complex cases, let's say that the flow has simply to pass from one side from the other one, we have to put none, because we don't have a transformation between the flow which enters let's say the master patch and exits the slave patch, and then we have to specify the neighbor patch, which is a slave AMI, of course, for the master AMI, and which is the master AMI for the slave AMI. And then the settings are pretty the same, except that we have to specify the construct patch and the neighbor patch and the name of the patch, of course. Sorry, this one. So this option must be set to false. Keep this in mind. So now we'll create the AMI patches. Perhaps let's have a look at the boundary file inside the polymesh. Now the master and slave patch are of type patch, so it's this is a generic type which cannot support the cyclic AMI boundary condition. Yeah, now let's run the create patch. I don't remember if I have to. Yeah, the create patch override. Let's load the OF6. Okay, so adding new patch master AMI, adding new patch slave AMI. So now let's go again inside the constant polymesh folder and let's have a look at the boundary file. So we'll see that the slave and master patch disappeared, and instead master AMI and slave AMI are created. You can create them by hand as well. Yeah, it's up to you. In order to have an automatic application, I prefer using the create patch, but the result is really the same. So now that we have those two patches with type cyclic AMI, we can use as a boundary condition for all the variables across these two patches, for example P, the type cyclic AMI boundary condition, and we have to put value internal field. And this is the same for all fields, because here there is not really a boundary condition. It's more a way of calculating fluxes across this interface. So what the let's say the arbitrary mesh interface does is non-conformal treatment of the mesh at the interface. So let's try to explain this. So OpenFOAM generally works with conformal meshes, does not support non-conformal mesh treatment unless you use this boundary condition. So you'll see that here you have, for example, here there is not one face is not connected uniquely to one cell is not connected uniquely to another cell by one face, but for example, this cell is connected with two other cells across the same face. This is called non-conformal mesh. So in order to calculate fluxes, OpenFOAM here calculates the flux. Let's say that we want to calculate the flux from this cell to these two neighboring cells. OpenFOAM calculates the flux across this surface, this cell face, and then uses a weighting in order to distribute the flux to these two cells. The weight is calculated based on the area that those two cells have with respect to this other area. So this is kind of the way that OpenFOAM, that AMI is working in OpenFOAM. If you want to use if you don't want to use the non-conformal interface, you have to use the sliding interface, which is different with respect to AMI. In fact, AMI is just a boundary condition, which does not, a way of calculating fluxes, which does not modify the mesh. The mesh is rigidly rotating, but it stays always the same. Are the fluxes which are treated differently across this interface. While the sliding interface, at each time step, decouples the interface, rotates the mesh, and then recouples the interface so that the mesh is always conformal at the interface, and then so that the flux calculation is done as always throughout all the mesh. For example, the sliding interface here would put an edge from this point to this point, or would change this point to this point, and put another edge here, another edge here, in order to have, let's say, another edge here, in order to have always one element face connected only and only to another element face. Yeah, so this is pretty much how AMI and sliding interface work. A sliding interface, in order to do this, has to do a mesh topology modification, because it's removing elements, and the connectivity matrix of the mesh is changing. So I think it's, I don't know which one is more time consuming, but for sure the sliding interface is a little bit more robust from the numerical point of view. Yeah, so now we are going to talk about how to set the AMI with the dynamic mesh dict. Now let's check the mesh, because we can exploit the fact that check mesh is writing the cell zone, is writing the regions of the mesh as cell sets. So now we have cell sets inside the mesh. We have cell sets here, region 0 and region 1. And let's see how the AMI is defined. So we define the AMI throughout the boundary condition and a proper definition of the mesh across the interface. And now we have to rigidly rotate the inner portion of the mesh And then the AMI will automatically account for this, account for the fact that the mesh is moving. It is the AMI is working the same whether the mesh is moving or not, because he always computes fluxes, as I explained before. So now we have just to set the rotation of the inner portion of the mesh, and we do this very simply by selecting the SolidBody motion solver and then specifying the region which we want to move and the SolidBody motion function that we want to use. In this case is the usual function that we had operated in the previous examples, in the previous tutorials, which is the oscillating rotating motion. We have to define the origin, which is the same. This is important. We have to design the mesh so that it complies with our motion. So I put the center of the cylinder at the middle chord of the airfoil. So I'll put the origin of the rotation at the same point, because if I don't do this, the mesh will the inner portion will penetrate the outer portion while rotating, because it will be rotating not symmetrically with the how do you call eccentricity, let's say. Then we have to define the axis, which is the y-axis, the amplitude, and the omega, which are really the same with respect to the previous tutorial. One thing that we have to pay attention is that the moving region is specified with a cell zone and not with a cell set. So here we do not have cell zones already. So we have to define cell zone. And that's why the check mesh is very handy, because it creates these two sets, which are basically what we need. In order to convert these two sets into phase zones, we have to use the set to zones utility with no flip map option. That basically this no flip map will not modify the surface normal of the mesh, will leave it all the same. So now we have, these are not needed, but we have these two new cell zones. So now if we go in the polymesh, we see that we have the cell zone. Now this, this I think it's a point zone, not a cell zone. Anyway, it doesn't matter. We have 4, yes. We will have region 0, region 1, 2 internal phase cells, and underdetermined cells. So we have region 0, which is the region which is rotating, so we can now select it from the dynamic mesh dict as region 0. If you want to see or have informations about the SolidBody source code, you can find it inside Home, OpenFOAM 8, SRC, Dynamic Mesh, Motion Solver, Displacement, SolidBody, which is this one, SolidBody Motion Solver. And you'll see that basically the SolidBody motion will rotate this is the constructor. We'll transform the points with the SolidBody motion function. So it's not anything complicated, basically. Then this is if move all cells, and this if we specify a cell zone, I guess. Okay, so now that we have everything done, let's run the case. Let's run the case. Yeah. We have to decompose the case first. We decompose part. I forgot this one. Okay, and then now we can run the pimple foam. MPI run np4 pimple foam parallel. What happened? Okay, so we another time we forgot to copy the 0 directory, so we can do it now. We can do it now. Shift P. Okay, so now we re-decompose the case. And we run the pimple foam. So now it's running correctly. As you see, this is a very poor mesh in order to have things working quickly. You can see the time stepping inside the processor folder, and yeah, let's wait for the solver to finish. So we have now the case almost finished. Yeah, this now let's talk about a little bit of this folder subdivision. I think it's better to have a more structured subdivision of the case in order to schedule all the operation, and always in the context of automatizing the case, as I did in the all run script, which basically sneaks inside all the folders and does things like creating the slave mesh, then the master mesh, then copying all into the solution folder, merging the meshes, and going for the pimple solution. Here in the script you'll find that at the end I'll reconstruct the case, then I'll go for foam to VTK, and then remove all the processor and time folders, so that the case is clean and we have only the VTK folder. And then you can open visualize the results, typing per-view and then opening the files in the VTK. Now I'm going, okay, the case finished. I'm going to reconstruct the case. So this will be very fast. And yeah, so I really like this way of operating in OpenFOAM, because it's very easy to do this. So it's worth doing it, unless we have to copy files, deleting, and in this way all the operation remains, and all the log files are printed inside the logs folder, which now is empty, obviously, because we didn't print any log file. Okay, so let's visualize the results. Now I'll use PowerFOAM. So yeah, so this is our case. Now you'll see that if I hit play, the mesh will rotate rigidly around the point I define, which is this one at the mid-chord. And yeah, this is another useful approach in the context of dynamic mesh. So we now I think we completed we closed the circle. In the first tutorial we talked about the block mesh and advanced use of block mesh in order to define a structural mesh, which is a little bit deformed here because we use this SnappyXMesh utility, but is still recognizable. So we talked about the block mesh. Then in the second tutorial we talked about the interpolating SolidBody with the slurp interpolation, which is it's been created after the 6 DOF SolidBody motion because it was a very good interpolation in order to move the mesh. Then we went through the displacement SBR stress and the displacement Laplacian, which are finite volume mesh motion solvers, which solve for an equation of motion of the mesh points. And in this last tutorial we saw this last approach, which is I think very useful. Yeah, now I think that this tutorial series is finished, and if you have questions or particular needs regarding other dynamic mesh motion solvers, let's say, let me know, that I will maybe create a video. But regarding an oscillating airfoil, I think we are done. So you'll find the case in the comments of in the description of this video, and I hope you enjoyed this series. And let's see for the next couple of tutorials.